Good morning. Hope you're doing okay this morning. Mr. Hunt, welcome. Good morning. We'll get started here in a few minutes, a minute or two, actually. All righty, well, my watch says it's time to get started. So let's go ahead and get rolling. I assume others will join us as we go through. Hope everybody's doing good this morning. Let me, where is my chat window? I know there's a chat window someplace. Just a moment. Ah, there we go. Okay. Hang on a second. I'm trying to get something set up here. Okay. Now. All right, let's get started. So let's talk a little bit about fixed point arithmetic. And before we get started on fixed point arithmetic, what I want to talk to you a little bit about is why you care. So everybody here has probably used floating point arithmetic, and unfortunately, probably you've used it in an embedded design. So what's wrong with floating point arithmetic? Well, the fact is that it's much slower than other types of math, in particular integer math. And the best way to explain that is that when you have a floating point number, let's say that I just wanted to add two floating point numbers. Floating point number in a microprocessor is not just a bunch of bits. It's actually a bunch of bits divided into multiple fields. There's always an exponent and a mantissa, just like you were doing scientific notation. And what you have to do, so for instance, to add, this is the same thing that you have to do when you're adding two numbers that are in scientific notation. You have to get the exponent to be the same. And that involves some manipulation. Then you can add, and then you have to figure out, once you've added everything, what the new exponent needs to be and shift everything around. And that's just for an add. And as we get into more complex operations, multiplication and division, that ends up chewing up a large number of CPU cycles. So what is a processor good for? A processor is good for adding and subtracting. Everything else that you do on a microprocessor is a compromise. And in particular, is good at adding and subtracting integers. So what you need to know when you're designing a real-time embedded system, math slows everything down, in particular floating point math. And it takes a lot more work even if you only use it a little bit. So let's say, well, I'm only going to use floating point math for this particular debug function or whatever. You just want to print some stuff out. It's no big deal. The problem is that once you start dealing with a floating point math, you now have a whole different set of registers that you have to save as part of the CPU context. So like the MSP432. So it can do floating point math relatively faster than other similar processors because it has a floating point unit. But those floating point units have multiple registers, and they happen to be 64-bit registers, so that's 8 bytes. You start pushing a couple of those, and now we're talking about bigger stacks. We're talking about every time we need to save context, there's more stuff to save and take on and off the stack. It's a big mess. On the other hand, we still need to deal with fractional values. There's no way around that. So the solution is learning about fixed point arithmetic. So what is a fixed point number? if, by the way, if anybody here has, I don't know if there's a good way to raise your hand on this chat, but if any of you have used floating or fixed point math before, you might want to put something down in the chat so that I can see that. So let's say that I have an arbitrary n-bit binary word. What gives it a value? It's just a bunch of ons and offs, right? What is it that we use to assign a value? Well, traditionally, if I have this 8-bit value that I have here, 011000011, traditionally, I would interpret that as the hexadecimal number 43, maybe the octal number 103. I can interpret it as a decimal 67 by using each one of the bits as, 2 to the 0, 2 to the 1, 2 to the 2, adding those all up and assign a decimal value to it. Or I can just call it the ASCII C, the ASCII character C. That happens to be a capital C. So what actually, I think, did I put down a capital C? 67 actually is lowercase c. Be 47 to be a capital C. But regardless, I could choose it to be a capital C, just not ASCII. The fact is that we assign arbitrary values to these binary numbers we hold in the computer all the time. So what if I decided that I wanted to interpret the value as 1/16 of the signed binary count? Okay. Then, so that would be placing a decimal point, effectively a binary decimal point, right there. Okay. So then I could note this in binary. I could call it this value. In hex, it would be 4.3, and octal would be 4.14. That's a little harder to see with octal. Because octal, we divided into 3 bits, right? So you got, that is 1, and pretend that you got 2 more digits there, so that would be 14. And decimal, 4.1875. How did that number get to be 4.1875? Well, let's talk about this. This notation for fixed point, we actually describe it in such a way that we call it Q notation. And so you see this Q 3.4. It means that I have 3 integer bits, 4 fractional bits, and the high order bit's going to be my sign on the 8-bit value. So in this case, my scale factor, we're going to call it 1/16. And the way that I get to that value is that everything over here, if this were a decimal number, so if this were actually 100.0011, the way that we'd interpret that is that we take everything over here on the right side of the decimal point and we divide it by what? We divide it by 10,000. So this is the fraction 11 over 10,000. Well, in binary, what we're doing is that we're dividing it by, in this case, 16. So the implied 10000. And so this is, if I take those 4 digits, that is 3. So it would be 3/16, which is 0.1875. So we're going to call this our scale, okay? And scales for fixed point numbers are all going to be powers of 2. And so in this case, it's 2 to the 4th, 1, 2, 3, 4, which is 1/16. So let's talk a little bit more about how we interpret this. So let's assume that we're using Q 3.4 notation. So our scale is 1/16. Let's say I wanted to represent the decimal value 4. okay, 4.0. So 4.0 in Q 3.4 is going to be that binary number, our 40 hex. So how does that happen? What we do is that we've got this scale factor that we've just created. So in this case, Q4, there's the 4, right? Oops. That implies our scale factor, which is 64. So we take whatever number we've got that we want to convert into this value, and we multiply it times that scale factor. So representing a decimal 4 in Q 3.4 notation, we multiply it times 2 to the 4, which is 64, which in binary is this, right? So let's double check our digits. That's 1s, 2s, 4s, 8s, 16s, 32s, 64s. Voila! And that in hex happens to be 0x40. So let's say using that same notation, I wanted to represent the value 1.62. So again, I'm going to multiply it times that scale factor, okay? 1.62 times 16. And that's going to be equal to 25.9. Now, as it turns out, because of the necessities of dealing with fixed point processors, not fixed point, but basically integer processors, integer math, we're going to always truncate when we are converting in this. We're never going to round. We're always going to truncate. So in this case, 1.62 times our scale factor is 25.9, which we're going to call 25, which we represent just like this. Okay? And so that is actually a 1.9 in hex. Now when we convert it backwards, okay, so now we're going to turn it back into a decimal value, see what that decimal value is. It's 1.56. So what I wanted to show you there is that it is this 1/16th, that's our precision, and that also sets our accuracy. So when I convert 1.62 to fixed point, I'm actually losing some resolution. Okay, so 1.62, if I were to convert that back from that value, I get 1.56. So let's take a look at the value minus 2.13. So again, I multiply minus 2.13 times 16, I get minus 34.8, which I'm going to truncate to minus 34, which turns out to be that value in binary. Remember, we're 2's complement. And when I convert it back, I get 2.125, which, hey, that's a little bit closer to 2.13 that I was looking for. But just take a look at this, precision. So before I move on to the next slide, you guys, does anybody here have any questions about this? I'll give you all a second to type in on the chat. I bet none of you thought we were going to sign up for math today as part of real-time embedded systems, huh? Okay. So I'm going to give you guys another way to think about this, because in spite of the fact that I got no questions, I'm pretty sure based on past experience that there are a bunch of you that are scratching your heads. So let's think about this as let's think about what a decimal value looks like when we're expressing it as a floating point number. So if I tell you that every value that I give you is going to be 100 times, oops, we got a non-muter here, there we go. If I tell you that every number that I give you is 100 times the value I actually mean, that would be a scale of 1/100. If I say 25, you're going to interpret it as 0.25. If I say 3.14, you're going to tell me pi. If I tell you -7, you're going to tell me, oh, you really mean minus 0.07. And if I tell you 3,583,771, you're going to tell me, no, what you meant was 35,837.71. So we do this in decimal all the time. What you're going to have to get your head wrapped around that's a little different is that now we're doing it in binary. Okay? So I don't want to do this. I already understand how to do floating point arithmetic. You put a decimal point, you write it in decimal, it prints out, everybody sees what they mean. I know how this works, right? Well, the first thing I'm going to tell you is that you don't really understand floating point, because the computer does not understand, for instance, 7.16. The computer has no concept of what 7.16 means. The fact is that somebody has written a program that takes the characters 7.16 and magically converts that into a binary format that the computer can deal with. Now, the reason that floating point math becomes such a big problem for folks is that floating point math is made to solve a very general problem. The general problem that floating point math is trying to solve is, I don't know how big or small the number that I'm storing is going to get. I know that I want it to be able to get arbitrarily large and arbitrarily small, and I want to maintain it to a certain number of decimal points. That's what floating point is all about. The fact is that in the embedded world, we can always frame our math to be within a particular range. And that gives us a huge advantage, because now if I know the range, then I don't have to deal with these arbitrary exponents that make floating point math work. So we talked about this a little bit at the beginning. In floating point math, you have to adjust and get decimals right. But in fixed point math, it just works. So if I want to subtract 7.16 or subtract 3.05 from 7.16, it's 4.11. And 716 from 305, it's still 411. I just have a different decimal place, right? If my scale were a 16th and I was expressing this in binary or hex, it would work the same way. Now, when I'm thinking about fixed point arithmetic, I have to think a little more carefully about scale, okay? So this is the decimal equivalent of doing a multiplication in fixed point. So to do that multiplication, I've got this implied exponent of 1 over 100 for both of these guys. And so I've got 3.07 times 0.4, and I know that that's ultimately going to equal to 1.48, but where do we come up with that? Well, if you take 371 times 40, okay, these two values here, and this value is actually 371 over 100. This is 40 over 100, or it could be 4 over 10. You multiply this one out, you multiply this one out, and then you say, okay, well, I want to get this back to this same divide by 10 scale factor. And so I have to divide top and bottom by 100 to get back there, and then I get back to my 1.48. So what's cool about this is that if I choose to do on a computer, it is really, really fast to multiply and divide by powers of 2, because I can perform that with a simple shift operation, which means that they become really, really cheap. And actually, on an MSP 432, you have a little bit even better operation, because this particular processor, if you go look at the details of how it's implemented, it turns out that it has a barrel shifter, which means it can shift an arbitrary number of bits left or right in a single instruction cycle, which is a really neat trick. So let's talk a little bit about notation and things that we want to learn about fixed point math. This is all testable, by the way, just so that you'll know. So we have this notation where we say, what is our word size? And how are we representing things? So there's always this mantissa and fraction section of the Q, so like Q 3.4 we were talking about. Or you might have Q 30.1, where you'd have one fractional bit, 30 decimal bits, and a sign. But your word size in a Q type value, it's always signed arithmetic for this notation, is always going to be the number of bits in the mantissa plus the number of bits in the fraction plus 1, okay? And for any practical system, when you add up this word size, it's always going to be a word size that is useful to the processor. So that would be 8 bits, 16 bits, 32 bits, 64 bits, okay? So what values can a Q m dot whatever hold? So the range of values, oh, that's a typo. That should be an F. Okay. So the range of values for this value is going to be, the smallest value that this can take on is minus 2 to the nth power. Okay. The largest value that it can take on is 2 to the nth power minus 1 over 2 to the f power. That's hard to say. 2 to the power f, we'll say it that way. Okay. The resolution of values. So this is basically what a 1 counts as, is 1 over 2 to the f. The accuracy for that you can represent with one of these floating, or with one of these fixed point values, is always going to be basically plus or minus half of a bit. Okay, or plus or minus 2 bits. That's the accuracy. So addition and subtraction, you have to have the operands to be exactly the same scale. And so you want to pick your scale primarily to match what you're going to be adding and subtracting. Now, as it turns out, when you do that, you're always going to end up with the same scale. So if you have a number in Q 7.8 notation, you're always going to get a 7.8 notation result when you add them. You just add them and it's there. So if you do multiplication and division, though, as we saw before, you're going to get a little bit different result. You're going to have to deal with the fact that you're also multiplying these exponents. And this is how it happens. So when you do a multiply, before you go back and rescale things, the result is always going to be, the scale is always going to be the scale of the first operand times the scale of the second operand, and basically the reverse on division. Now, what you do need to know about is saturation. And saturation is when that fixed point number reaches its highest or lowest value. And so, much like anything in computers, we have to be aware of the values that we're trying to combine mathematically, because we don't want overflow. Once you get an overflow or you reach saturation, you no longer have something that you can keep track of accurately in math. So this is all well and good, and you can certainly write fixed point arithmetic, and I've done fixed point arithmetic for years, where I actually wrote all the functions to do the adding and subtracting and multiplying and dividing. But as it turns out, Texas Instruments, this is one of those things where I'm going to sing their praises, has provided us with a library. It's called the IQ Math Library, and what I want you guys to do here between now and Wednesday, I want you to go through and I want you to take a look at section 2, and in particular paragraphs 2.1, 2.2, 2.3, 2.5, and 2.6 in the user's guide, which you can get online. And I want you to look at that and start getting a feel for what sort of things and notation they provide in the IQ Math Library. Okay? So let's talk about a practical example. So we've got our little edu board here. And I'm looking at part of the schematic for the edu board. And this happens to be the accelerometer. And you'll note that it has these A to D outputs here that go up, and they go up to the processor. And on the Launchpad processor, they are coming in J3, 23, 24, 26. So if I look at J3, 23, 24, and 26, those are all analog inputs. And they are all referenced to 3.3 volts. So from the data sheets, what I know about this particular accelerometer is that 0 G's is going to be at 1.65 volts at 25 C. Now that's going to vary over temperature, but we're going to figure that it's 25 degrees C wherever we are. It's connected to these pins. We just saw that from the schematic, and it's connected to the MSP432 here. And we have a 14-bit A to D converter with a reference voltage of 3.3 volts. So let's say that I want to know how many G's of acceleration I'm experiencing in a particular axis. So I know that given this information here, that if I want to find the output voltage for that particular acceleration, I take the actual acceleration, multiply it times 660 millivolts per G. Where did I get that? Right there, the sensitivity. And I'm going to add an offset of 1.65 volts. So my A to D count, as a function of voltage, because this is a 14-bit A to D, is going to be 16,384 divided by 3.3 times the voltage. And if I go in and I do substitution here with these two equations, I end up with my count being equal to this. And multiplying that all out, I get this bloody mess. And so I'm going to move acceleration over here onto the left side. I'm going to divide both sides, and eventually this will simplify out. You can see some real simple things right here. This 3.3 is going to drop away. This 16.84 is going to drop away. So now, to convert millivolts I convert millivolts to volts, multiply it all out, and now my acceleration is going to be the count minus 8192 divided by 3276 times 1 over g. And if I get rid of all my division operations, my acceleration in g is now going to be 3.0525 times 10 to the minus 4th times the a to d count minus this offset. So how do we decide? So now we know what this is in floating point. Now we're going to have to figure out how do we want to deal with this in fixed point arithmetic, because right now everything that I've done is floating point because that's the way I'm doing my math. It's actually decimal floating point. So the first thing I need to do is figure out what size values I'm going to use. So the full range on this A to D, on this analog device, this accelerometer, is minus 2.5 Gs to plus 2.5 Gs. Okay, so if I did a 2-bit range for my mantissa, that'd give me a value that would work from minus 2 to plus 1 for my mantissa. Well, that's not going to cover that whole range, right? If I do 3 bits, then I cover minus 4 to 3. So minus 4 to 3, that works. So my mantissa needs to be at least 3 bits. Now the full range of output is a total of 5G with an A to D converter that has a maximum count of 16K. What that says is that 1 bit is 0.305 millig's. Okay? And so we see then that, okay, if I do 11 bits, can't quite represent 1 over 3277, which is that. So I would be losing some of that resolution. If I go 12 bits, 1 over 4096, so that's pretty close there. So I need a minimum mantissa of 3 bits. I need a minimum fractional component to not lose any information of 12 bits. Okay? So the Q math, by the way, assuming 16 bits, their notation drops the mantissa piece and only keeps the fractional piece. So that's what this notation means. So if I were to use 16-bit values, I could pick a Q12 or Q13. Okay, that would give me at least the minimum amount of resolution. And in a 16-bit, if I did Q13, 16 bits, that gives me 3 bits, and this gives me 4 bits. So if I do Q12, I'm going to have this range. If I use Q13, I'll get that range. I got a lot more flexibility if I use the 32-bit IQ math. And the 32-bit IQ math, we're now looking at, again, I can do IQ 12, right? Or I can do 29, which gives me a huge amount of precision, but a relatively limited range. Now, for an MSP 432, one of the things that we discovered when we were looking earlier this semester at 432, one of the things, if you recall, that we discovered is that 64-bit math is 32-bit math, excuse me, 32-bit math is its most efficient way of doing arithmetic. So we definitely should just go ahead and default using 32-bit values, the IQ. If we did the Q math, which is using 16-bit values for fixed point, that would be more appropriate for like an MSP 430, where it does where doing 32-bit math involves a little bit more work because it has a 16-bit accumulator. But here we are we're on the MSP 432. And at this point, I'm going to pick kind of a compromise between this 12 and 29. It gives us some extra fractional resolution. So if I'm doing divides and that sort of stuff, when I'm manipulating these values, I don't lose resolution. But I also, if I need to multiply on some intermediate operations, this IQ 20 is going to give me a little bit more headroom so that I don't get an overflow. So let's talk about how we make this work, writing some real code. So you have to include the IQ math library, obviously. Now let's do some constants. So this is my scale in G's, right? So we figured that scale, 3.0525 times 10 to the fourth, right? And where is there? 3.0525 times 10 to the fourth. Okay. So that's my scale. Okay. And then this is, why have I done this with the two offsets? I've got this offset. Okay, so that is offset. This is two different ways of computing offset. Okay, so let's look up here though. So how do I make this number as a constant? So if I have in my IQ 20, I can express this guy. If I multiply top and bottom by, if I take this 3.025 times 10 to the minus fourth, if I multiply this times that huge decimal number, 10 to the eighth, right? Now I can express this as an integer with no loss in IQ 20, and then divide it by that 10 to the eighth to get me that decimal value that I'm looking for. So this is a way with constants, without ever using a decimal point, to express this value, okay? And then I have to get my offset both of these will do the same job. Don't know why I did them both that way. Okay. So let's look at this guy. In essence, you know, this is, we're just trying to find that offset that we're going to be doing to do our conversion. So I've got these variables that are going to hold my acceleration value. Okay. They are IQ 20s. Now, when I read these values, so there's my reading the A to D value, I'm going to use my IQ 20 multiply. Now, this particular library function takes IQ 20 values and multiplies them. It is really important to know what the scales are. We talked about that a little bit earlier whenever you do multiplication. So you have to know, in this particular case, this is assuming that I have two IQ 20 numbers that I'm going to multiply. So I'm multiplying these two values. So that's the scale times what I read on the A to D converter, and I'm adding in the offset. I do that 3 times for my 3 axes. Now printing becomes a little bit more of a challenge, right? And the reason is that I have to, there is no printf function for fixed point numbers. So I have to print out manually what I'm going to do for the mantissa and the decimal point. So to print out that value, so let's say AX. This guy right here, that is, I want to take the integer portion of the value that I have in grab X. And in this case, I'm going to take the fractional portion of, and I want 4 decimal places, so I'm going to take the fractional portion of that value, so that's just the fractional portion of that IQ, and I'm going to multiply that times 10,000 to get this value right here, and you have to put in your own leading zeros, otherwise it looks really weird. And so now I can print these out as decimal values with fixed length notation. So when I get ready to use this, so that's actually, I think that's as far as I want to go today. I have a little bit here on the using the graphics display, but I think I want to go ahead and stop here today. And we've got about 10 or 15 more minutes if you guys want. I'll give you guys a chance to ask questions. And I'll just unmute everybody. See if that works. Are there any questions? I can't wait for the pop quiz. You guys are all going to know this. All right, well, there being no questions, I declare class over. We'll get this posted if anybody wants to watch it again here in sometime this morning. Y'all have a great day, and we will see you on Wednesday.